I mentioned that there's, in addition to the SLAC foundries, the argon foundries, those are really focused on solid state qubits. So you can see here the tools that have already been installed in the argon foundry. Again, deposition, etching, lithography, metrology. So this is a national user facility. And some of the key accomplishments in the past year and a half since we've built it and be able to use it include being able to create large-scale diamond membranes, be able to deterministically position spin qubits in diamond membranes, be able to transfer those membranes to other materials, for example, silicon, and then be able to do integrated devices. So here are some nano to microscale photonic cavities that have been created in the argon clean room. And then in addition to the foundries where you can make quantum devices, there are also facilities at Stanford, at SLAC, and at Argonne as part of QNext where you can characterize those materials. So some of those facilities include the X-ray beamline like LCLS, LCS2, ultra-fast electron diffraction if you want to be able to do kind of ultra-fast characterization of your materials and systems. I think one of the exciting things is you don't need to have just the material itself. You can have kind of the full quantum circuit or quantum network and be able to characterize that on some of these beamlines. And if you go to qis.slack.stanford.edu, you can see the user proposal program needed to access some of these SLAC and Argonne facilities. And then in addition, there are capabilities at Stanford, in particular in the electron microscopy area. And like I said, we have these electron microscopes that are optically coupled. We also have a new Nion electron microscope that allows for millielectron volt electron spectroscopy. So very high resolution electron microscopy and also very low vibration. So especially if you want to look at quantum materials or quantum excitations like magnons or phonons, I think this new TEM that should be arriving at Stanford soon will be very exciting. So just in the last 3 minutes that I have, I wanted to highlight a couple science innovations. And this is by no means an exhaustive list, but one of which is that atomic scale optical characterization of defects using optically coupled TEM. This is a TEM that was installed actually earlier this year that allows for basically atomic scale, I think 0.07 nanometer or sub-angstrom imaging resolution of materials in reactive gaseous environments with light, with some spectroscopy capabilities like electron spectroscopy, also EDS spectroscopy. So I'll highlight one research accomplishment there, focused mostly on materials. Then I'll also talk about some of the fabrication efforts that have given rise to kind of integrated solid state optically addressable spin qubits based on some of these silicon 2D material heterostructures that have been enabled by using the SLAC foundries in the Stanford clean room. And then finally, I'll have just a quick slide on what SLAC is doing basically to detect dark matter using their superconducting qubits. So as many of you know, color sensors are promising sources of single photons in future quantum networks, but they're actually quite heterogeneous in terms of their spectral emission. And the origins of the heterogeneity are largely unknown. We know there are color sensors, but we don't know precisely what the defects are and what their environment, their local crystalline environment is that might be changing the spectral energy that comes out. And here, for example, is a plot showing, for example, the wavelengths that can come out in various single photon emitters, for example, in a two-dimensional material like hexagonal boron nitride. So here's a capability that you all would have access to. It is a university facility that allows for transmission electron microscopy combined with optical spectroscopy. So here you can see the